Everyone again, Michael Goen here. I'm going to kick us off by covering what's new. In vLLM, we had 2 releases since we last had office hours, 0.9.2 and 0.10.0. A couple of big things there. We had over 93 new contributors within the month, which is always great to see. We had a lot of performance improvements for NVIDIA Blackwell, B200s, GB200s. We're still working a lot there, but we've made really good improvements. We've been working very strongly on improving the startup time experience, so reducing both startup time for cold starts and warm starts with vLLM to better optimize for auto scaling. We landed support for EPLB, or load balancing for expert parallelism, which obviously will be important as we go through scaling MoEs with llm-d with Rob, Tyler, and Clayton later in the session. And we landed initial support for supporting the responses API from the OpenAI API for the future of model usage. As I already mentioned, the session today is on scaling MoEs at very large scales. The next session will be on the new hybrid memory allocator architecture in vLLM, which is paramount for how we support the modern LLM architectures that have non-uniform attention on the different layers, or don't just use plain global attention. And we're ready to hear more sessions that you want to have. We have plenty of people we're planning with, but if you would like to present something that you're doing with vLLM or working on and contributing in the project, we'd love to hear you out and host to. So to start us off, just a quick refresher on what is vLLM if you're not familiar. It's the fastest growing de facto standard for open source model serving. It's an LLM engine and server for serving open source LLMs across a variety of architectures and hardware. That's been heavily adopted by the open source community, by industry, and by researchers. That has turned it into a very active, substantial project. And part of the reasons why it's become so popular is that it supports 100+ different types of models, all the key state-of-the-art model families, inference, systems research. Usually, it comes from a fork of vLLM. They publish a paper, and then usually, we get those contributions back into the project. So it moves very quickly with the speed of research and use in inference in open source and with industry partners. And of course, it gets great performance on NVIDIA GPUs, but it also generalizes and offers backends for AMD GPUs, Google TPUs, AWS, Intel, Huawei, and other hardware accelerators, making it that sort of general interface for all these various different model architectures and all of these different types of inference optimization features to run on all these different types of hardware accelerators that are available. And as I kind of alluded to before, we're not just hosting text-only large language models here, but multimodal models with hybrid attention implementations, embedding models, reward, re-rank models, so taking care of inference during post-training workflows and fine-tuning workflows like RLHF. We support many different types of quantization, even more than listed here, so with custom kernels and various algorithms in vLLM and the surrounding projects like LM Compressor. We have many custom, authored kernels in vLLM using, advanced, kernel libraries like Cutlass and Triton, and we heavily rely on, infrastructure like Torch Compile in order to offer us ways to keep the model definition very simple, PyTorch and Hugging Face based, but still extract great performance through graph compilation styles using Torch Compile as our hook. Of course, many different types of inference systems level optimizations like disaggregated prefill, chunked prefill, prefix caching. These are supported as first-class citizens, and constantly more are added week by week. And of course, many different level application level features like tool calling and structured outputs, and various other things you can see in the API definition to make sure that applications moving from closed source APIs to vLLM and other open source APIs have a very smooth transition. And finally, scaling your model deployments beyond hosting on a single device, but running efficiently on multiple devices inside of a node, or even across multiple nodes with different types of tensor, pipeline, expert, data parallelism, and disaggregated prefill as well that we'll talk about here. You know, a lot of features packed into vLLM to scale your workloads across all of the accelerators you have available. A little bit of a reason, a little bit of explanation about why Red Hat's here. You know, both myself, Tyler, Rob are at Red Hat. We come from Neural Magic before and joined the Red Hat team. We've helped work on many various features in vLLM, and we're all committers on the project and work on a lot of things in terms of pushing performance, reducing CPU overhead, implementing production level features, and of course, helping with model compression and pushing forward you know, cutting edge research like quantization in order to make deployments more efficient with vLLM. So with that little preamble out of the way, we wanted to give you an update on some recent vLLM related blogs that came out recently. So please check them out here in the slides. So the three of them are sort of a comparison between ollama and vLLM. You know, talking about which one is good to use in different use cases. You know, ollama is really useful for local developer inference. vLLM is more necessary once you want to scale into production. Also a blog on Eagle 3, which is a state-of-the-art speculative decoding method, and how vLLM now supports it and what kind of performance it now can offer. And then another sort of application level blog on how to use vLLM on macOS for developer inference. So what's new in vLLM? So first I'm going to cover the 0.9.2 release. There's a lot of things here, but briefly I kind of want to highlight that we finally support in the V1 backend of vLLM, priority scheduling, embedding models, which have been a long work in progress, in Mamba 2. We've also been working hard on enabling full CUDA graph execution, so moving beyond just supporting piecewise CUDA graphs with the initial V1 launch. And we're working on generalizing this to all the attention backends. Another thing I'd mention is the Flex Attention backend has seen a good amount of development, and now it actually works as a very general backend that can support any head size and even FP32. So it's a good fallback when we don't have, you know, efficient like flash attention kernels or flash infer kernels for supporting models with weird head sizes, or for the weirdos that want to run in really high precision. Yeah, lots of models added in this release. As I mentioned, a lot of hardware optimization, particularly on NVIDIA Blackwell. This was the first release that supported SM120, so that's the RTX Blackwell. So if you have like a 5090 card in your desktop, or a RTX 6000 Pro, that's finally supported. And as well as updates to, you know, the NVIDIA, you know, the Intel GPU backend, AMD ROCm, seeing a lot of performance improvements, especially on the intention kernel side, and TPUs getting more flexibility and more performance enhancements, finally supporting not requiring the head dim to be divisible by 128.
Hey, Michael, before you continue, can you please put a link to the public slides either here and I can share it, or I can't find anymore?
Yeah, sure. Let me.
A few people are asking on YouTube live chat.
Yeah, let me just get my.
You can just share them with me and I can put them in there. You can continue. Thanks, man.
There they are. Yeah, and so this was a release where EPLB was landed, which was a big work in progress. A big performance enhancement for using expert parallelism in production. Several quantization things. We finally added NVFP4 support through compressed tensors, so expect to see a lot more FP4 quantized models ready for optimized deployment on Blackwell. We're working on cranking them out. We also added some new OpenAI endpoints, specifically translations, API and have been working on generalizing and improving the usability of the transcriptions API, particularly useful for new models in audio, large language models like Voxtral. And one thing I'll just note, if you've used the compilation config CLI before, or -o commands, there's now more flexible expression and parsing for those using a dot syntax. So if you use those, I highly recommend checking out these PRs. Next, onto 0.10.0, another big release, over 300 commits and 60 new committers. This is obviously a major release for us, and is when we started officially deprecating v0 and starting to remove those parts of the code base, as v1 has implemented most things by now and has gotten relatively stable. A lot of model releases on this release, and a really key thing that was added to v1 was sort of the introduction of async scheduling, so allowing us to overlap this engine scheduling on the CPU with the inference actually happening on the GPU runner. We still have more work to do here, more things to make asynchronous, like the preparation for inputs on the GPU. But we have to start somewhere, and plan on also supporting this with more features, like speculative decoding is not supported with it yet, and other things. Another important feature is we pulled out the definition for local attention, or particularly chunked attention, for Llama 4 out of the Flash attention backend and generalized it across the different attention backends, so allowing for that optimization to work for more backends like Flash Infer and Flex Attention, which is pretty helpful for Llama 4 users. And some big improvements to startup time reduction. I actually came up with this frozen garbage collection one that should greatly improve startup time, especially for small models. And also an interesting enhancement on expert parallelism called elastic expert parallelism landed. Expect to see a lot more work there. It's an interesting topic. Finally, of course, many more enhancements to hardware. Like I said, we've been pushing a lot on Blackwell SM100 optimizations, getting a lot of kernels from TensorRT-llm integrated, and new Cutlass cuDNN kernels, optimizing the various key workloads that we want to support well on V200s. We also did a minor version bump for PyTorch, the latest 2.7.1, and yeah, we hope to upgrade to 2.8 when it comes out in a few weeks. And two performance improvements I want to call out. So there's a micro batch tokenization improvement on the front end API server. This really helps with heavy, prefill heavy, prompt processing on the front end. I think, yeah, it's like a huge improvement for small models being overloaded on the server side. And also a specific improvement for a fused kernel for DeepSeek models that improves performance a surprising amount. And then there's some updates to quantization and hardware support as well, of course. TPUs finally support FP8 KV cache, which has been a feature requested by some users there. And we've been working on optimizing the per token group quantization using Triton, and now finally CUDA, offering a big performance uplift for DeepSeek models, or also Qwen 3 models that use the block FP8 quantization. And this is also the release where the responses API was implemented. So if you're interested in using agents or things for that, please start playing around with that, using it, and letting us know what we can better support. So that's all I have to cover here. Thanks for bearing with us, and I'll now pass it off to our special guest.
Tyler, you want to kick off?
Yeah, I wasn't sure if you wanted to do the intro. Let me share the first slide here. we are here. Yeah.
You can go ahead.
Yeah. How does this look? Okay, so one of the things we're covering today is DeepSeek model support in vLLM, and then also llm-d. And this includes, a lot of other like similar models. There's a lot of overlap between DeepSeek, Qwen, Kimi, etc. DeepSeek brought a lot of different kind of like novel things to open source large language models. One of them is multi-latent attention, which really compresses and changes the like compute to memory ratio of attention in favor of compute, which makes sort of more efficient. It also changes the way it's a sparse MoE with many experts, and so it's sort of like more sparse than MoE models of the past. So this is one of the things we're focusing on today. It also brings speculative decoding, so MTP built into the model. And also they, in their deployments of, in their architectural deployments of DeepSeek, they do prefill decode disaggregation, which we will focus on today as well. Okay, so first of all, what is an MoE model? So in an MoE, we replace a dense feed-forward MLP with a sparse one. So each token comes out of attention into this router. The router picks a top K weight, top K, or a number of top K IDs and top K weights for each token, routes it to a couple of experts. The experts are linear transformations, and then they come out of the experts and they're combined together according to their top K weights, and then also added to a shared expert. So many models coming out these days. Really, most of the large ones, or really all of the large ones, are a mixture of experts models with a large number of experts, maybe 256, 384, and a smaller number of experts selected per token. I think 8 for a DeepSeek v3. So yeah, DeepSeek v3, R1, the Llama 4 series, the Qwen 3 series, Kimi K2. All of these are this style of MoE model. And so like, this is sort of like the workflow of the MLP layer. So coming out of attention, like I said, we go into this gate. The gate is the router that selects the expert IDs and the weights for each token. Both the hidden states, top K IDs, top K weights, are fed into this expert-wise MLP. And then these are all summed together. The outputs of the expert-wise MLP are summed according to the expert weights, and then added to the shared expert ID, like I said. And I kind of want to frame this as like, there's a bit of a rework of the way vLLM deals with MLPs and this of MoE models and the style of MoE models that are supported. So here, we have in the title, dense MoEs. So all MoEs are sparse. However, kind of earlier ones, like the ones talked about in the MegaBlocks paper, or I think like a mixtural model, have like a really like smaller number of experts. So like here they give an example of like 3 experts, top K1, where it makes sense to, you come out of the router, you do a permutation, you do computation, which are like there's a few styles of this. You can do a batch matrix multiplication, or you can frame it as a sparse matrix multiplication. And then you combine them together. And with this, we used to do, we had one kernel for MoEs called the fused MoE. We did tensor parallel sharding. So the MoE is 2 layers, 2 gems really. And the first in this case would be a like column parallel linear. and the second would be a row parallel linear, and you shard the intermediate size. So one kernel, simple to tune and implement, but it doesn't really scale to multi-node very well. And it's okay with the expert imbalance. But what we've seen is really a transition to these sparse MoEs with hundreds of experts. And so here's an ablation study that shows like why you might switch to a sparse MoE. So this is from DeepSeek MoEs towards ultimate expert selection and mixture of expert language models. And we can see just as they increase the sparsity and number of experts, the scores really increased, which is why we've seen really like a transition to these really sparse MoE models. And it looks like Rob has dropped to deal with movers. So this transition from like dense to sparse has really changed like how you need to implement these models. So instead of this like larger intermediate size, we have a really small one. The kernel has a like pretty low performance because they're really small, each individual expert. And then like small problem sizes per expert. So this like tensor parallel sharding that we did for like a mixtral doesn't really work the same way anymore. The other thing is they're just really big. So the memory footprint is very large. The tensor parallelism requires like 2 all-reduce operations per layer. This is just like really bandwidth heavy. It involves like every token involves every GPU. And it's just it doesn't scale. So we need to scale better. So to address this, we really have like 3 key changes in the way we execute MoE models. So we go from this tensor parallel mode that doesn't scale and also like gives you bad problem sizes for the expert kernels to this style of execution where we do data parallel attention and then expert parallel MoEs. As an aside, this is especially important for MLP models, or sorry, MLA models, because if you do tensor parallel in a DeepSeek, you end up replicating the KV cache. So that's sort of like doubly there is a reason to use data parallel attention. And then we do, instead of expert parallel, and then instead of like the all reduces, we use this expert parallel communication. And then we need to do some optimizations on top of all of this. So we've got expert parallel load balancing, and we also are working on in vLLM overlapping the communication and the computation. By the way, do we have any questions in the chat? I haven't been paying attention to it.
No, not at the moment.
Okay, so I will continue. Okay, so I mentioned this transition from tensor parallel to data parallel attention plus expert parallel. So this is sort of what it looks like. So we, you can think of each GPU will be a different data parallel rank. Each GPU will have their own attention buffer and their own page attention. We do sort of request level parallel in attention, and then between attention and the MoE layers, we switch from sort of this request level distribution of tokens to a expert distribution of tokens. And so what we have here is we have this dispatch operation, which looks at the top K IDs for each token, sends them to the corresponding expert, where we do the experts. And then after we apply the experts, we hit this combine operation, which according to the top K IDs and the top K weights, sums up the results and sends it to the next layer's attention. And sort of like the really big benefit here is that these dispatch and combine ops are sparse, right? Each token only needs to involve top K, which is like 8 GPUs, or 9 for the source as well. instead of having to involve all of them. So it scales better to multi-node. Okay, and then so like here is sort of like what the kernel workflow is. So here we have got 2 DP ranks, we've got hidden states. The router has given us 2 expert IDs for each token. We then dispatch to the experts according to the expert IDs, and then afterwards we combine them, taking into account the expert weights. And so we've got a couple of implementations of these dispatch and combine ops. So in their open source week, DeepSeek released these DPP, dispatch and combine. And both of these use nvshm, which is a library from NVIDIA. And there's like 2 flavors of this. So there's sort of like a normal mode that's used for prefill or for training, that's really optimized for high throughput. And then there's this low latency mode for decode, where you have this like static shaped buffer, which has like the maximum number of tokens you could use. And so that's really targeted for decode. So the normal one doesn't support CUDA graphs, is slower if you use a really small number of tokens, and then the low latency mode basically works with CUDA graphs, is optimized for a smaller number of tokens, optimized for latency, and then the memory requirement if you use it for prefill would be way too large. And then we also have another set of kernels, or another kernel from Perplexity, which is a dispatch and combine operation, really the same operation, also uses nvshm, but it's a little bit more portable, a little bit more flexible, right? DPP requires that you use exactly 8 GPUs per node, but it's, kind of like maximizes performance. PPLX is a little bit more operationally simple, and it is CUDA graph compatible, and we sort of find that it is like nicer to use for really like the chunked prefill case, where the DPP kernels are sort of optimized for the disaggregated prefill decode. But both of them are useful. So here's a performance plot, if you can see it. So here is the Perplexity kernels. Here's dispatch, here's combine, and they really outperform the DPP kernels in the single node case, but then in the multi-node case, the DPP kernels really shine. So and then like there's also just niceties to PPLX being operationally simple, and then like kind of nicer for the chunked prefill case for a couple of reasons. So there are reasons to use both of them. So kind of the lower levels in the experts, we kind of have like a couple of different like styles of implementing the actual experts. So as you kind of start to see, we sort of have this sort of like exploding number of styles of implementing the gems, the different communication ops. But so for the low latency case, we end up using these batch gems because we pad out the size of the activations to support CUDA graphs really. And then for like the throughput case, we end up with these group gems where the activations will be different sizes. And like the buffers in memory will be different sizes. So these are like really kind of like different sort of styles of gems. And then as we continue, we've got a lot of different kernels developed. So we're working with NVIDIA to add support for NVFP4 models. So we kind of have like a lot of different kernels that we need to plug into this framework. So what we've done is we've implemented this sort of like modular kernel framework to support all of the different cases: Perplexity, DPP, batch gem, grouped gem, Triton gems, etc. So And here's sort of like a workflow. I'm not going to like dive into like this flow chart, but here's a workflow for the like fused MoE high throughput and low latency case, I believe. But like sort of like what we're doing here is we've sort of boiled it down into like a few basic building blocks that you can plug into. So we've got basically like 3 phases. One is prepare. So prepare is, and by the way, it's not just the like we didn't just fit the like deep like the dispatch and combine style of executing MoEs. We also are adding the like tensor parallel, permute, gem, unpermute style. So we sort of have like we're trying to do like one framework for all styles of MoE execution here. So the prepare is like a dispatch, which we have 4 different flavors of, or it's a permute, which we have a couple different flavors of. And then we do the experts, and then we have this like finalize, which is combine, or it's an unpermute. And like the goal here is to really make it easy to like plug in different implementations under the hood to these like different pieces. Okay, so one of the things that we find for these like large scale MoE models is if you kind of like execute these naively, you get like a lot of load imbalance. And why this is just because the router will happen to assign more tokens to some of the experts compared to others. So what we have in vLLM is, and I think Bowen Wang is still in the call, is called EPLB, which periodically rebalances the expert placement, and it also like replicates some of the experts. So like the way that we've been executing recently is like you add 32 additional experts and then replicate the heavy hitters, and this over time you become like more and more balanced in terms of like the load of assignment to different experts. And this was also like something that was released by DeepSeek during their open source week. And then we've got a prefill decode disaggregation. Rob, do you want to jump in at this point?
Yeah, sure. Can you
Okay.
guys hear me okay? Yeah.
Yeah.
So I'll go quick because we're running low on time, and maybe I can just give the high point. But as Tyler kind of mentioned, especially when we're looking at these wide EP setups, the prefill instance and the decode instance, really want to be configured differently. Like Tyler talked about, for instance, DPP, having low latency kernels that are really optimized for decode, and high throughput kernels that are more optimized for prefill. For us to be able to kind of exploit all these, we really want to, be able to configure the prefill and decode instance separately. So one of the things we've added to vLLM over the course of the past couple of months is this PD disaggregation kind of setup, leveraging the Nixel library from NVIDIA. So, an overall request flow kind of looks like this, where we have a proxy that gets the request. The proxy decides that this request should be processed with prefill decode. It adds into the body of the request, these KV transfer parameters that really tell the prefill instance, okay, just process the prefill and then leave the decode alone. After the prefill, kind of finishes, we send it back to the proxy. The prefill instance sends some additional metadata about which engine it is, about which block IDs, are being used in the KV cache, and it appends a do remote prefill, argument that gets sent to the decode instance. And then the decode instance, as it's processing, rather than running the prefill itself, it executes a read transaction, using that metadata that the prefill instance provided to read the blocks from the remote. And we use Nixel, which is a really nice user interface that operates on blocks, to pull the KV caches from the prefill instance to the decode instance. Nixel has quite a few different backends, but the most commonly used one is a library called UCX. UCX is a really well developed and pretty mature communication library which supports different backends. So far we've been very focused on InfiniBand, which is a high performance networking from NVIDIA, but we also work with Rocky, TCP, and then have been looking into some other backends like EFA, for instance, which allows us to really support a very heterogeneous network topology to deal with this overall transfer. So ultimately, this PD disaggregation is an important optimization to really allow us to configure the prefill instance and decode instance separately, which is really important for these wide expert parallel models, which has such a big difference between how we want to process the prefills and how we want to process the decodes. And then one other just side note is inside of vLLM, we've implemented all of this to be asynchronous. Let's skip over this for now, just because we're running low on time. Maybe we can jump to like the llm-d side. I think the major kind of piece, we still have some more optimizations that are going on, but I think the major piece, and hopefully it's pretty clear, is when we're running these wide EP deployments, it's pretty complicated. Like we're gonna have a really big set of nodes that need to be coordinated together. We have prefill instances and decode instances. We need to have a proxy in the middle that's making smart decisions about how to process an individual request. This is a much more complicated deployment than what you see from a traditional kind of single replica of vLLM. Throw a deployment out there, throw a service in front of it, do naive load balancing, that we see as a pretty standard way to run vLLM. This is a much more complicated deployment pattern, and so this is one of the reasons why we've started the llm-d project, and one of the key workflows that we're including in the project. So I'll pass it over to Clayton. Clayton has been a great partner of ours from Google, leading up a lot of the inference serving efforts across GKE, and we've been really working closely with the Google team to bring together the vLLM and Kubernetes community to try to make it easy to run a variety of different deployment patterns on top of Kubernetes. So I'll pass it over to Clayton.
Thanks, Rob. And I'm really happy to be here. I am not an ML engineer by background. I worked for the last 10 years on Kubernetes and helping people, run massive web applications and giant distributed databases, by providing lower level systems that make some of that higher level running big complex workloads easier. And so when, as we've been working on the GKE side, what we saw was there was plenty of people running in production, very large scale, large language models, all the way from small models, all the way to very, very large models. And as serving has gotten more complex, as Rob and Tyler were describing, there's a huge opportunity to bring more intelligence to different parts of the stack, but you don't just want it to be all thrown together and be one big ball of mud. You want to come up with good boundaries and good components. You want to understand like what the real pain points are, and you want to tackle those specifically. So if you can jump to the next slide, there's a lot of experience that's scattered out there in the ecosystem internally at Google and other large serving providers and folks who built model as a service backends on what are some patterns that show up time and time again. And so I think there's a huge opportunity for us in vLLM and in some of the communities around Kubernetes that are trying to improve these areas. So we find good primitives that we can use, not just for one monolithic project, but can be used by many different people. YDP is a great challenge. It means you've got all of these nodes coordinating, but if one fails, you might need to restart all of them. Well, there's things that we can do to improve that. So the llm-d architecture is a very, very simple idea, which is you've got a whole bunch of replicas. Those replicas are pretty complex internally. Sometimes those replicas are going to talk, such as with prefill decode disaggregation. When they talk, you stop having like nice simple problems like, can I get this memory to move across nickel to another machine? And you get, that machine doesn't exist anymore. It was shut down 35 seconds ago. And some of what we can do before those requests hit those replicas is have an understanding of where load is going across all the replicas and channel it. So a project that we started last year was the Inference Gateway project. And it's all about just doing smarter load balancing, because you've got all these different long requests and short requests. You've got different workloads, some that are latency sensitive, some that are throughput sensitive, and you want to distribute them evenly and keep all those machines humming across replicas. Now, with llm-d and some of the work that we're doing around wide EP, and it's about how we keep each of those individual replicas running efficiently as well. So you might have traffic between replicas for prefill decode, but you might also want to increasingly start using much more advanced prefix caching. You can only hold so much in the GPU memory. You can spill some of that to CPU, and you can spill even more of that to local disk. But at some point, you may actually want to distribute that, to spill it to hosts that are uncorrelated with your serving instances, so that all the replicas can pull equally from them and you don't have performance hotspots. Auto scaling is a really, really thorny problem. Across the industry, very, very few people in production serving today are auto scaling. Why? Because it's a hard problem. Because you're not just trying to tackle one factor like we did for regular web services. It's just, I'm running out of CPU, give me another worker. Sometimes you can get nonlinear effects. For instance, if I scale up my prefill workers, I can saturate my decode workers because suddenly more traffic comes through. So as a project, we want to work on helping to standardize some of that auto scaling and look at not just the individual parts, but help pull together that big picture of, I need this much more capacity because the replicas are reporting how many different types of requests they can take. Or we can understand, when we have queuing, or we have, Tyler mentioned there's load balancing within replicas. If you have some replicas that are receiving more queries that are causing them to be more unbalanced, at a higher level, we can distribute requests away from that. And again, if you jump one more slide, there's a lot of things that'll happen in the next year as we scale up with MoEs, as more and more people start serving these much larger models. Our goal with the project is just to find patterns that work for multiple people. And there's lots of different ways to do these, and we're going to keep discovering new ways. But can we bring people with similar problems to roughly similar ways of solving the problem, kind of bake those best practices in? And these are our well-lit paths. So we've got 3 right now in our 0.2 release that came out this week. These are our first 3 paths, but the first one is, can we distribute better than random requests that go to individual replicas? So that's intelligent inference scheduling, looking at the request, looking at how busy the model servers are, and understanding the differences between 2 different requests, one with long context and one with short context. Also prefix-aware routing, which is a popular feature. This is another way to say this is smart routing. We've integrated this all together. It works natively with vLLM. It's not perfect, but we're adding a bunch of features around that make it something you can kind of just turn on for any model and get a benefit. Rob mentioned PD disaggregation. It's still big and hard, and there's a lot of different tunings. Our goal is to help people, understand the rules of thumb, because it's going to be different. If you're running small models, you're not going to get as much benefit from PD disaggregation. If you're running very, very large models like DeepSeek, there's a huge advantage because we can specialize the software. So the well-lit paths that we have are helping guide people through some of those trade-offs, and we'd like to improve and generalize so that if you see those benefits in more scenarios. And finally, wide expert parallelism, as Tyler talked about, is making it possible in vLLM at scale to run the very large multi-host decode and prefill instances and have it work out of the box in a production setting. We're not quite there yet. The testing that we've done initially is on H200s. And there's others in the ecosystem that have succeeded at this. Our good job is to really pull that together so that most people in vLLM can go from 0 to serving DeepSeek in these large configurations very easily. And we'll get there soon. So Rob, I want to turn it back to you, actually, as we're almost at the hour.
Yeah, Tyler, did you want to try to show the live version?
I can. I have it up. So
we can also go over the hour, guys. It's okay.
Yeah. Okay. Let's do it. All right. So this, I'm sure, is too small of text. Let me zoom it in. Let me close these. So how is this like text size wise?
Could you do like maybe 2 more clicks?
Yeah. Okay. How is this? So yeah, where we are right now is we're in llm-d infra's quick start. And we're in the wide EP example. And I've got some just file workflows for kicking everything off like pretty quickly. But let me do a kube control get pods here. And so you can see the pods in my namespace. So what I have deployed right now is 1 prefill node and 4 decode nodes. So what this is it's wide EP on the decode. So DP32, EP32, and the prefill node is DP8, EP8. And I've got, so we've got, this is the gateway. Gateway uses gRPC to talk to the EPP and then routes requests to the individual nodes right now. And then finally, I've got this interactive benchmark pod that I can use to run requests just from inside the cluster, just as a matter of convenience. So let's use a Stern just so we can see some logs. So here we've got prefill logs up above, and then down below, let's get some decode logs. And then let's exec into our interactive benchmark pod. And then here I've got a file, just a shell script, run.sh, which just does a sweep over, let's change this. Let's do 2048. But just does a sweep over benchmarks, over like synthetic data. Here I'm just setting the input length to 128. Output length is 2048. This is just because I'm really just trying to measure the output throughput of the decode instances, and the prefill one is just there to make sure we can run it, and the PD transfer just kind of is functional just for this kind of simple benchmark right now. So we do run.sh. Actually, what I'm going to do is let me just run just one command. Sorry. Let's do so let's do max concurrency of 2048. Let's do 2048 requests. Let's do an input length of 128, and then let's keep the output length pretty small for this this run. Let's run more requests though. This is using the benchmark serving script in the vLLM repo. It does take a little bit because it has to do this initial prompt test run. Yeah, there's not that much to the demo. I do have a Prometheus metrics dashboard up as well that we can look at.
I think dashboards are cool.
Yeah, yeah. Let me. Once there's something there, that actually might be broken. First of a live demo. One of the things that you can see is as we run, we're logging the balancedness of the expert parallel load balancing. So you can see here we have max tokens across EP rank of around 24 500-ish, and the average is about 1,000. So you get this balancedness metric of around like 0.4. As we run these things, it will increase to about like 0.6, maybe 0.7. I think there's a lot of like room to experiment here with like the amount of replicated experts. But yeah, it is running right now. And we can see each of these is one API server cross one engine core within like this combination is 100 tokens per second, but there's like 8 times 32 of these.
Tyler,
So-
could you throw up the K-get pods for a second, like just to show what's in the namespace?
Yeah. So I did that right at the beginning, but I don't have it up.
Yeah,
right.
No worries. I mean, I can see it, but like one of the things I just kind of want to like highlight is, we have I kind of showed in the original, kind of PD disag, like that proxy component, which is, a really critical, kind of part of this overall system. And I think, one of the key things we're trying to do with llm-d is create like a separation of concerns in between these individual components. So one of the things that's really nice about this is, this is using a production quality, proxy, with Envoy at this level, and with EPP, which is the, kind of scheduling logic, we're able to kind of use all the existing scheduling algorithms that, Clayton was talking about in our first well-lit path, where, we still want to look at load balancedness. We still want to look at, for the prefill worker and the decode worker, whether you're going to get a prefix cache hit or not. We still want to look at, all of those, kind of key components that we had in the, kind of first well-lit path. And, by having this modular architecture, we can put the wide EP, component when we go to deploy, but, we're able to kind of leverage all the existing like load balancing, scheduling logic, et cetera, that has been built up in the ecosystem, over a long period of time. So I think this is really like an important kind of key point, to know what we're trying to do, as opposed to, rewriting our own proxy, rewriting our own scheduler logic for each one of these individual use cases. It's a really key part of the overall design of the system. And when we say, okay, the llm-d is Kubernetes native, this is really what I mean. Like, we're using the existing components, we're using that modularity, in the overall design.
And to add one more point to that, Rob, even something I didn't really emphasize is, you can always write your own proxy. You can go a long way with writing your own proxy in Python or Go. Eventually, you will hit a point where everyone else is angry at you for writing your own proxy. And so we decided to skip all of that and say proxies like Envoy, even Nginx, HA proxy, are extremely good, battle tested, and they handle all those things so that we don't have to. And by splitting out that, make the decision about where the request goes. We've got two pieces. We can let them be the experts at that. We're showing this in Kubernetes here, and not everybody does deploy in Kubernetes. I always want to call that out. There's plenty of people who will never touch a Kubernetes cluster and be happier for it, and that's okay. Some of the mindset that we had, even in the as we were building out this gateway, which is basically just Envoy plus a process that's telling us where the requests to go. There's nothing here that's truly fundamentally dependent on Kubernetes, except the APIs that make this dynamic to allow you to reconfigure it, and the APIs that react to failures. So if one of the decode instances went down, the orchestration would bring up another replacement, and then you stitch it back into the load balancing. So even though today, like, our focus is on making this work in Kubernetes, we're not intending to approach this from the perspective of you have to use Kubernetes to get these benefits. It's just a place to start. And we kind of expect that, the vLLM community, which is much broader than just people who use Kubernetes, will appreciate that.
All right, and the benchmark is done. We see we got around 20,000 output tokens per second. This is a pretty small scale run for this cluster, right? There's like 4096 requests, 4096 concurrent. We actually are running into a bunch of benchmarking issues. Like, I cannot get enough requests into the system to saturate it right now. But it definitely needs at least like, 16,000 or so is like where we're thinking of like concurrent requests for this setup of a 5-node cluster. I also ran a GSM-8K run. This is kind of like the standard eval we do for inference. It's grade school math, sort of like what you would do in 3rd grade, like Johnny has 3 apples, Sally took 2 of them, how many does he have left, that kind of thing. We do this because it's a generative eval, which is really nice. And then we can see that R1 did very well here with a 97%. And that's the demo. So yeah, back to you, Michael.
Yeah, pretty cool demo. Thanks a lot for that. We have some questions in the chat. I think this was when Clayton was presenting. So a question from Atharva: what about better than round robin requests? And how tunable is the intelligent routing? Is tuning required?
So the answer is it's very tunable, which is we've got a couple of really simple scoring mechanisms, but it's kind of set up the way that a classic scheduler in the literature would be set up, which is you have an incoming request, and then you apply a set of scorers on all the backends, and you say, which backend should I send it to? You end up with a few, and then something at the end makes a choice between the ones that are good enough so you don't get hot spotting. That's pretty classic across load balancers, but our focus is, well, we're so early in this, people are going to want to tune it. We want to make it really easy to extend. So it's written in Go. You can extend it by adding new Go schedulers, building your own, and then turning your scores on and off. You can also dynamically reconfigure it. We know a lot of people probably will have tweaking for specific workloads, like long context workloads. They might want to make different trade-offs. So some of that's already there. The future we're looking for is we'd like this to be a default component that works for most people. And then we also want to allow people to do rapid experimentation to come up with new algorithms that assign load based on those request characteristics. And there might be many, some we have today out of the box: KV cache awareness, prefix cache awareness, LoRa adapter awareness. So we concentrate on the LoRa adapters. There's plenty more that the research community is going through. We'd like to enable people to integrate those in. So pretty darn flexible.
Yeah, I definitely like to see the focus on making it accessible to researchers. It's definitely paid dividends for vLLM itself. There's a question from Yakub. Many serving techniques assume NVLink connected GPUs InfiniBand. Are they also I guess how effective is disag prefill for PCIe or 10 to 100 gigabyte networks? Which I think that one's maybe a reasonable ask. The maybe interconnect between nodes.
Yeah, this is actually one of the things that I really like about Nixel and UCX is that UCX does support a quite broad range of actual physical hardware in terms of the networking. And I think the mental model for KV disag is if you're cutting it close with respect to the KV transfer time as it relates to the end-to-end latency, you probably shouldn't be doing PD disag for that request. The mental model should be that the request is going to take 60 seconds to process 1,000 tokens or to do a prefill of a certain size. And so we really only want to be doing PD disag on requests where the time to transfer is actually pretty small in context of the overall end-to-end request time. And that's part of what we encode in the intelligent kind of scheduler is the decision about, does this request make sense to do PD disag on? But the truth is for 0.2 of llm-d, we really focused on the InfiniBand and remote transfer or an RDMA based transfer. We have been working on some implementations that use TCP, and one of the key things that we have for the 0.3 release of llm-d is validating this. And as Clayton kind of mentioned, a key part of what we see as the well-lit paths in llm-d is defining the boundaries of when certain transports will make sense, right? for really, really, really long requests, we think that TCP will be able to make sense in, but there's going to be some point in time where it won't. And so that's a big part of what we're trying to do with the 0.3 is investigate a few different transports and really try to put the parameters around, how much networking do you really need for which models, for which, request patterns. And so that's going to be a big focus of the upcoming ones. But so far we've validated things on the, RDMA based networks. So right now, yeah.
Yeah, okay, makes sense. Thank you for that. And one last question, is there room for non-trivial further performance if EPP runs as a sidecar or WASM plugin directly inside the gateway instead of as a separate pod?
So the assumption that we kind of make is when you're processing of a token is a single token is taken, tens or hundreds of milliseconds. The call out from the envoy to the endpoint picker to the scheduler is about, it adds about a millisecond of latency on fast networks. So we don't spend too much time on that. One of the limitations of WASM would be the memory addressable. So, some of what the scheduler is doing the classic trade-off of you have this envoy tuned for millions of concurrent requests and super low memory overhead. And then you have these requests that you can maybe run 10 of them at the same time per host. And what you're looking for is, I've got all this memory and CPU free. Can I do better than random by throwing CPU and memory at the problem? So the answer is nothing we've seen says that even calling halfway across the world would really impact the overall latency numbers. Obviously, you're going to run this close to where the load balancer sits. But that being said, Envoy does have WASM support, and there may be parts of it that we actually want to carve off and make it easy to run inside WASM plugins. WASM just adds a little bit of overhead to the development process, so it hasn't been a concern for these production settings yet.
Okay, cool. But yeah, nice that the flexibility is there. Well, yeah, we are decently over time, but thanks everyone for dealing with technical issues and yeah, staying for this talk. We had over 100 people live watching, I think 150. So yeah, thanks a lot for coming in today, and thanks to our speakers for showing a very impressive technical talk and demo. Thanks everyone for coming back.
Thanks,
And,
Clayton, for coming on.